All right, so beginning again at the start, we are still left with the deformation theorem to prove, all right? So what the idea here is you're looking at two counterclockwise, maybe that's what's wrong. Maybe I've forgotten the, no, they're both counterclockwise. So this one goes like this, and this one goes like that, right? Over here.
On your game, the game, they're not both counterclockwise.
They're not.
One side's clockwise.
Oh. Okay, I'm an idiot. So, all right, this is the problem. Now, here, these are both counterclockwise, all right? But the what I need to apply is I need to use Green's theorem on this annulus, or this region between the two curves. So, all right. So let's start with the region. So we're going to assume that, as pictured is right. This is gamma out. This is gamma in. Or I've called them gamma 1 and gamma 2, all right? Okay? My claim is that those integrals are equal for a closed form. All right? And so what we have to do is we have to look at the region between, so let me just draw another picture over here of the picture. So this is the region S. The boundary of S is, on the one hand, it's gamma 2, but it's union with minus gamma 1 because gamma 1 is going the wrong direction. So the boundary, positively oriented boundary of a region, it's supposed to be such that when you're walking around it, the region's on your left. So if you're on the outside counterclockwise edge, the region's on your left, but you had to go clockwise on the inside in order to keep the region on your left as you imagine yourself. All right, so that's the boundary of S, which is oriented, the positive boundary of S, which is S being this region between the two things. And so we have the following, that the integral over the boundary of S of p dx plus q dy is equal to the double integral over S of, qx minus py. That's Green's theorem. But because this is closed, because it's closed, qx is equal to py, which means that this is equal to 0. So what that then gives me is that the integral, this is of course equal to the integral of what? This is itself equal to the integral over gamma 2 of omega plus the integral over minus gamma 1 of omega, here omega being p dx plus q dy. So since this plus that is equal to 0, it then implies that the integral over gamma 1 of omega is equal to the integral over gamma 2 of omega. And that is known as the deformation theorem. Now, you can ask, the real question then is, how did I know that that was Green's theorem? Because Green's theorem, you may or may not have seen Green's theorem stated for a region with a hole in it, right? So that is where those crosscuts come into play, right? So like you can take, basically the idea is this. So you take the region that looks like this, right? And you cut it into two pieces. See, the top piece and the bottom piece, they're both simply connected. And so you put in these crosscuts, so this way up here, and this, and then on the bottom. So you can't just add area integrals without cost, but when you add the integral over this way and that way, it's the same set of points, but it's oppositely oriented. So when you add the line integral over omega of those pieces, you get 0. And so then essentially you do Green's theorem on the top, and you do Green's theorem on the bottom. And when you add the Green's theorem on the top to the Green's theorem on the bottom, you get the integral of the area over the whole S, and then you get the integral over the boundary of the half regions. But the boundary of the half regions becomes the counterclockwise outer boundary, but it ends up giving you the clockwise oriented inner boundary. So inner boundaries have to be clockwise oriented, but outer boundaries have to be counterclockwise oriented. That's how we define the positive orientation. That's this boundary of S. Is it by default takes inside boundaries to be clockwise oriented, whereas outside boundaries have to be counterclockwise oriented. And so in that, if you make that definition for the boundary of S, and you understand that little argument, then this gives you Green's theorem for.
Like on the left.
Yes, yeah. So I'm just sketching the proof of Green's theorem for a region with a hole is what I just was talking about. Anyway, this is the deformation theorem. So how does this apply to us? Well, just to give you a simple example, example 1 would be something like we had omega equals to y dx minus x dy, was it? X squared plus y squared. Do I have the signs right on that? I can't remember.
Yeah. Oh, I think we have a plus one on top of that. For the argument or omega?
Minus y dx plus x dy. So I got a minus here. Minus y dx plus x dy is what I had, right? And we saw that the integral over the circle, right, in the counterclockwise oriented fashion was equal to 2 pi, right? And this is closed on the punctured plane. So so that means that you can, so we've got this, here's our circle, right? Here's the origin. And you can take any curve you like, inside or outside of the circle, as long as it encircles the origin, like that. This one, right? I'll call that gamma 2. Or you could put gamma 2 out here. As long as it's, counterclockwise oriented, right? Then it's going to be true that this is also going to be equal to the integral over gamma 2 of omega. So the fact that we know that the integral around the circle is 2 pi, and that we know that that form is closed between the unit circle and any curve inside it, as long as it doesn't we have to encircle the origin, I believe. We get that they're equal. See, what would be the problem if I tried to not encircle the origin? What happens? What's the problem with that? So like, what if I put, here's my unit circle, right? Here's my origin, right? Suppose I tried to make gamma 2 like this. What's the region between gamma 2 and the unit circle now? So as you can see, well, it's not that it's, I'm dropped star shape here for the moment. I'm talking about simply connected, which means, every loop can be deformed to a point. In other words, there's no holes in it for the plane. But here, the problem is the region between the unit circle and gamma 2 contains the origin, and that's a point where the form is not closed. So we can't apply the deformation theorem to these two curves. That's the problem. And that's good, because what is the integral around gamma 2 for omega in this case here? It's 0, right? Because omega is closed on the region encircled by gamma 2. Yeah. Okay.
So why did you throw a star shape?
Well, I'm proving things in the star-shaped case, but it is true. Every theorem that I've said about star-shaped is true for a simply connected region. It's just I don't want to. I don't want to give you the full. The proof in the star-shaped case is more manageable because we have the star center, and so we can make explicit arguments, using that. All right, so let us move along here. We've already talked about harmonic conjugate before, but the way harmonic conjugates are talked about in Gamelin is a little bit different. So let's look at that. So here's his lemma. This is lemma 3.3.1. It says that if u, which is a function of x and y, right, is harmonic, then minus partial u partial y dx plus partial u partial x dy is closed. So what does it take to show that that's a closed form? Yeah, I mean, this is true. I would like to, it would be nice to just talk about the exterior derivative in here, but I'm trying to behave since not everyone knows about that. But what it means is that, so here's my P, here's my Q, right? For it to be closed, I need Py to equal to Qx, right? So let's see here, partial y of minus partial u partial y, right? Is that equal to partial x of partial u partial x? Well, this is going to be true if and only if what? Minus uyy equals to uxx, right? But that's true if and only if uxx plus uyy is equal to 0, which is, in other words, u is harmonic. Right? So if it's harmonic, then it's closed. All right. Now, so let's see here. Oh. And then, of course, there's a converse direction, right? Now, the converse theorem requires what? Well, no. Could you say the other way around? Given that u is given that it was closed, does it imply u is harmonic? And the answer is sometimes. All right. So here's the fine print. If this is actually not the converse. Curses. I think we could go the other direction, though, if we said if it was closed on a star-shaped region. Then I do think that implies u is harmonic. But I shouldn't get into that at the moment. Here's the theorem that we're supposed to do. U is harmonic harmonic on star-shaped domain. All right, then there exists V, the domain is D, okay, V on D such that U plus IV is holomorphic on D. This is theorem 3.32. All right. So, all right. So we've got its harmonic on a, okay, so I guess if it's harmonic, then it's closed, right? So we know U harmonic implies minus partial U partial x dx plus partial U, oh, good grief, y, not x, partial x dy closed. Let's see here. Closed on D. But we know that closed implies exact on a star shape, right?
Yes.
So there exists H such that what? Such that DH is equal to, well, I don't see how that's going to get me the V though.
Choose a reference point.
Oh, well, okay. So I guess I did do that. Oh, dummy. So see, this would have been obvious to me if I had done it the same day we were doing the other proof. So let me think through this here. Use harmonic, that means that's closed, right? Okay, so let's not do the there exists D. So that implies that so the claim is that the V is actually equal to the H, all right? So like V, well, let's say it this way. I'm going to say H, and we can do integral from, A. So I write down H of B is equal integral from A to B of, this thing minus partial U partial Y dx plus partial U partial x dy. So this is here, the picture. Here's my A, here's my B, right? It doesn't matter which path we go because it's closed implies path independent. And, all right, then what? The claim is that that's the V. My proof is incomplete here. I've hung myself out to dry in my notes. Okay, so my claim is that this is claim. This is equal to V. All right.
This is talking about differentiating with integral sign and using plus equations to obtain it.
Okay, so yeah, don't worry. We can get it here. We can get it here. So my claim, this is a claim. Actually, this is a definition. So let's let v be defined by this. All right, we'll take the integral to z, v of z. All right, great. The point is, we already know, like the constructions we worked through the last class, we know we can do this. And what else do we know? We know that partial v, partial x is equal to minus partial u partial y, and partial v partial y is partial u partial x, because those are the p and the q of this thing. All right, so it really goes back to that thing I drew the pictures and motivated that the potential function defined by integration gives you the correct partial derivative formulas, right? Partial p partial x, partial v partial x is the p thing, partial v partial y is the q thing, but in this context, those are also what? Partial derivative of u with respect to y with a minus, partial derivative of u with respect to x with a plus. Of course, at this point we go, aha! But these are the CR equations for f equals to u plus iv. And since we have the Cauchy-Riemann equations holding over the star-shaped domain, which is of course open, includes an open, it's an open connected set, so that gives us that f is holomorphic on this thing. So, hooray. Yeah. There wasn't much missing from my notes. It's just like, there's like an extra sentence. All right, so it's unfortunate I didn't get to this the same day I did that proof. Okay. Theorem. And I have an example where I actually, you're like, wait a minute, that means that we could calculate the potential by doing this integral. Well, yes, you could. I mean, you can calculate the harmonic conjugate by doing that integral.
Yeah.
So, example 2. So if we had, u equals to, say, x squared minus y squared, then v would be the integral from pick your favorite point, I'll pick 0. So this is, by the way, harmonic on the whole complex plane, right? Yeah. So we could do the integral from 0 to z of, what am I supposed to do? What's the minus partial u partial y? Okay, yeah, let's get to it. That's 2y dy plus what? Partial u partial x is 2x, so yeah. Oh, that's a dx. 2x. Yes, but there's a minus in the formula. So minus partial u partial y dx, which is 2y dx, and then plus partial u partial x dy, which in this case is 2x dy. And so you go, well, you know what that is? That's the integral from 0 to z of the differential of xy, which is just going to give me, and this is z equals x plus iy, of course. So this is just going to give me xy. There's a 2 here. Sorry. Yes. So 2xy. So therefore, u plus iv equals to x squared minus y squared plus 2ixy, which, by the way, is z squared, is, holomorphic on the complexes, right? And more than that, 2xy is the harmonic conjugate of x squared minus y squared. So, yeah, it's another way to calculate harmonic conjugates is what it is, all right? And in some sense, it can be better than what we did before. There's a more tedious example in my notes. I'm going to go on. So the next thing is the mean value property. Is that you or me? Yeah, I don't have a. Sorry, wrong number. Okay, well, all right, great. So mean value property. You might call it the average value property, right? Here's the definition. Let H be continuous on domain D. Let Z naught be in D such that, the disk Z in C such that modulus of Z minus Z naught is less than rho. All right, suppose that's a subset of D. Then the average of H of Z on circle Z minus Z naught equals to rho, all right? Oh, I said R actually, sorry, R, not rho, equals to R, is A of R equals to integral from 0 to 2 pi H of Z naught plus R e to the I theta d theta over 2 pi for 0 less than R less than rho. So this is our definition of the average. All right. So does this make sense? I mean, maybe, maybe not. Let's think about it. So you've got Z naught, right? And then the circle of radius R, right? Typical point on here has the form Z naught plus R e to the I theta, right? And you can do that for 0 less than or equal to theta less than or equal to 2 pi, right? And so if you integrate around that, so I would tend to calculate an integral with respect to arc length by default. So what would the arc length integral here look like? It would be this ds, right? But what is the relation between s and theta? See, s is equal to r theta, right? So like ds is r d theta, which is little r here. If for a circle, r is fixed, So if I did an integral over ds, then I would divide by the circumference to be fair, right? If you're going to calculate the average over a circle, then you should divide by if you do the integral with respect to arc length over the circle, you divide by 2 pi r. So if you do the integral with respect to theta, you only divide by 2 pi. So that's where this definition is coming from. And now there's something very interesting that happens here. Oh, you got me. Thanks. So, so let's see here, some calculations. First of all, the integral from 0 to 2 pi of h of z naught d theta is equal to what? 2 pi times h of z naught, right? Because h of z naught is a fixed constant, whatever it is, it is. So, in other words, we can say h of z naught is 1 over 2 pi times the integral from 0 to 2 pi of h of z naught d theta. All right, great. And so we can use this identity in what follows. Check this out. The modulus of a of r minus h of z naught. Right? Well, this is going to be the modulus of the integral from 0 to 2 pi of parentheses h of z naught plus re to the I theta, right, minus h of z naught times d theta over 2 pi. So what I did was I just brought the 2 pi in here, and so like this minus h of z naught becomes, you know, h of z naught over 2 pi d theta integrated from 0 to 2 pi with a minus, and then just factor that out. And so, but then this is less than or equal to the integral from 0 to 2 pi of the modulus of h of z naught. Oh, excuse me, I say modulus, but I should say absolute value. Here we assumed h was real valued, right? I may not have said it, but it says it. So I should have said let h be continuous, real valued, you know. So here h was a function from d to r. That was stated in the definition. Okay. That was stated in the definition, and I failed to write it down. Sorry about that. Let's see here. So here's the theorem. If U is harmonic on disk D, and if the disk Z such that modulus of Z minus Z naught is less than rho is contained in D, then U of Z naught is equal to the integral from 0 to 2 pi of U of Z naught plus R e to the I theta d theta over 2 pi. So what is this saying? This saying is that if you have a harmonic function, its average, right? And I guess the question is, what do you mean by? Well, okay, so the proof of this basically is to use the. Well, let me go through the proof. This is very surprising. The value of a harmonic function at the center of the circle, right, at z naught, is equal to the average of its values around the circle. The value, so like we have z naught in the middle. This integral is looking at the values of u on the circle, right, of radius r. And it's saying that the average of u on the value around the circle of radius r is equal to the value of u at the center of the circle, provided that this circle fits inside the domain on which we know u is harmonic. Right? Yeah, it is kind of weird, I think. Okay, so what's the proof of that look like? Here we go. We let u be harmonic on D. Right? And then we know that minus uy dx plus ux dy closed. Right? And hence, let me call this omega. Omega is exact, right? and the integral around the circle centered at z0 with radius r of, this thing, minus uy dx plus ux dy, well, that's equal to 0, right? Because an exact integral, the loop of an exact form around a circle is 0. And then I say, the theorem essentially follows from this identity. We just need to write the integral in detail. Okay. So let's see here. So you got the circle, z0, and, modulus of z minus z0 equal to r. So we have, let's see here. Well, how do I write this? Okay, so let's see here. These integrals can be done as arc length integrals, right? So what you're looking at, this is equal to the integral from 0 to 2 pi of, partial u, partial y of, now the dx is what? So here, x equals to x naught plus r cosine theta, y is equal to y naught plus r sine theta, parameterization of the circle, right? So dx is what? Yeah, minus r sine theta d theta. Dy would be r cosine theta. And so what we got here is dx is what? Minus r sine theta. So I can, so I pull an r out here up front. And so what you've got is partial u, partial y sine theta plus partial u, partial x cosine theta d theta, right? And then, a little bit tricky, but remember that partial, y partial r is sine theta, partial x partial r is cosine theta. So this is partial y partial r, and that is partial x partial r. So by the chain rule, what we're looking at is integral from 0 to 2 pi of partial u partial r d theta.
Which is just u. Well,
Which, to be more specific, is, so then we goodness gracious, we rewrite this just a bit. I'll bring the partial derivative outside of the integral, and we have integral from 0 to 2 pi of u of z naught plus r e to the I theta. I mean, that's, I'm omitting some details in the calculation above, right? And what is that? Somehow I got a 2 pi. I think, dividing by 2 pi, right? So this is all equal to 0, right?
yeah.
So anyway, this is equal to 0, right? So let me just say that implies, I'm going to ignore my notes for a second here, and just point out that implies that the integral from 0 to 2 pi of u of z naught plus r e to the I theta d theta over 2 pi is equal to 0. Right? What does that say? So this says that A of R is constant.
AR is constant.
Because this is A of R. We showed that this is A of R, right? So if partial derivative with respect to R of A of R is 0, it's constant. But then what happens is the limit as R goes to 0, what do you get? But what happens to this? As R goes to 0, what happens here? You just get h of z naught integrated over d theta for 2 pi. You just get h of z naught again. But what was that? But that, right? So, oh, but that's also equal to that. Yeah. So, H, I'm an idiot. Ay, ay, ay. That is the worst. Yeah. So again, just to emphasize what this, it says that the average of values of a harmonic function on a disk is the value of the function at the center of the disk, which is really kind of a bizarre thing, like you said, right? Yeah. And so, just to, full disclosure here, this step I did, pulling the partial derivative from inside the integral to outside the integral, I'm using something called uniform continuity of U. We haven't really justified that, but this is a theorem of analysis for sufficiently nice functions. You can commute the order of partial differentiation and integration. That's not always true.
Is it like the reverse of that Feynman thing?
It's kind of the reverse. It is the Feynman integration trick. Okay. It is that. That doesn't hold for all functions in all contexts. And then finally, definition 3.43, we say a continuous real valued function h of z in a domain D has the mean value property if for any point z naught in D, the value h of z naught is the average of h of z over any small circle centered at z naught. Yeah. So a function that has this property, that the value at a point is given by averaging values of the function of little circles around the point. It's said to have the mean value property. So that brings us to the maximum principle, all right? And so I will have to stop here because we're out of time. But so anyway, I'm going to make a small video to get us back on track here. Yeah. So hopefully that video will cover the maximum principle, and I'll also do a couple of examples of the conformal mapping. So you guys have, that's for your mission 4. But again, mission 4 I bumped back to Wednesday because we are a little bit behind.